Okay, so please watch my first 6 minutes because I thought I recorded all 55 minutes and I didn't. So the first video goes over finding functions and it ends as I was saying we're getting ready to look at sketching. So if we have r vector r of t and we have from t comma 1. T is in the x place and 1 is the y. The 1 is always going to be 1 no matter what t is. But if we want to find, well, what is r of negative 3? Well, it's going to be negative 3, 1. What is r of negative 1? Well, that's going to be negative 1, 1. And I try to make sure my angle brackets don't look like parentheses. R of 2, well, that will be 2, 1. 5, 1. And we could do this for so many different vectors. So now, once you have your vectors, you can write points for all your vectors because from the origin, that vector is going from the origin to a point, and those points are the same, the points would come from those vectors. Okay? So you have those points. So now if I want to graph, what I did was, and I did this in my first video, so I started here and I said, well, when t equals negative 1, that's going to go over negative 1, up 1, and I have my vector to it. When t is positive 1, whoop, and my vector to positive 1. Even when t is 0, when t is 0, the y value is going to be positive 1. And I did that. I did it on the right. I did it for 1, 2, 3, 4, and 5. To the left, I did negative 1, negative 2, negative 3, negative 4. This is positive 3. No, this was positive 3. So this was positive 4. This was positive 5. And so on. You could keep going, and all of them would go up 1 on the y. So then I looked at another vector r of t from t, and then the y component was t cubed minus 10t plus 7. So anything I choose my t to be, that'll be what the x component is, and then I have to substitute it in to find the y component. All right, so I did some of them here, and I should have done them in order, but I just started. I was like negative 3, negative 1. So when you substitute in negative 3 into here, that's where the 10 come from. For the negative 1, that's obviously going to be your x component. So when you substitute it in, we get 16. In my 55-minute long video, I went through all of that separately, but it's already written. So now, these are vectors, but they can correlate to points as well. So when I go to make my, I'm going to erase this. When I go to make my vectors, when when t was negative 3, I went up 10. So I went up to 10 and put my point. When r was negative 1, that's where I went up 16. I don't look like I don't have that anymore. So it would be about like, oh no, it's here. That's it. This is it. 16. I kind of went over a little too far. When t is 2, it was at 20 or 19. Negative 2 was at 19. R is 0, or when t is 0, we had 0, 7. We had t of negative 1. When t is negative 1, it was at 16. Oh my gosh, sorry. When t is positive 1, it would be negative 2. When t was positive 2, it was negative 5, which was about here. And then when t was positive 3, it started to go back up again. And so I sketched this graph. It was kind of like my goodness, my drawing, which I'll say, all right, so it look kind of like that. And again, I'm not as, like, we have calculators now. We have graphing devices, apps. We can graph all this. I really just want to make sure we are all understanding, though, the correlation between a vector and its point. Um, and all the things as we move forward, making sure we can pick the normal vector from an equation and pick a point from it and all of the things. So number 1 and 2, these first two were in the form where we had the x component was just t. Okay, but sometimes neither component's going to be a t. You'll have something going on. So the first one was in the form of t and then a function of t. Sometimes, though, we just have two different functions of t. And so what that means is you'll just substitute into both of those. So now, when I look at this is r of t, vector r of t, 6 cosine t, 3 sine t, what we see here is you can look at that and tell, oh, that's going to give me the shape of an ellipse, where it goes through my x's at -6 and +6, and my y at 3 and -3. And then I went through and drew all my vectors. So I drew my ellipse first, and I give myself a really hard time about my drawing, but I feel like you guys at this point, you know what an ellipse looks like. So even though mine is a little off center, you know. And then I went through and I did all my vectors. So, you're here, that's 0. And as we go around, we have our pi over 8, 2 pi over 8, which is just pi over 4, 3 pi over 8, then pi over 2, 5 eighths, 6 eighths pi, which is 3/4, 7 eighths pi, 8 eighths pi, which is just pi. And if you think about that, if you know this is pi, like when you get back around, that's also 0. It could also be 2 pi. So then 9 pi over 8, we have 10 pi over 8, which is 5 over 4, 11 pi over 8, 12 pi over 8, which is 3 halves, 13 pi over 8, 7 pi over 8. Actually, this should be 7 pi over 4. Look at me going back over it. I catch my mistakes. 15 pi over 8, and then, like I said, 2 pi. So, another sketch. And another, like looking here, it wasn't just a t. You had like a g of t and a h of t for your components. So now in this one, we see we have an x component, a y component, and a z component. None of them are just a t. So you're going to have, you could pull out different things. But when we look at it, I want us to pick out, well, what do we see? This is the equation of a line going through a point, which the point we can tell comes from the constants. So 2, -1, and 3. And then the coefficients for t, that represents the vector. So this is an equation of a line that goes through the point 2, -1, 3, and is parallel to the vector -4, 5, and 1. So what I want us to recall is that when something is parallel to the vector, that means it could be the line. The vector is on that, can be on that line. There is on that line. So I first start with plotting the point 2, -1, 3. So I went and I graphed 2, 1, 2, -1, 3. So to kind of show you what I did, I'm going to erase part. So this wasn't there. I went ahead and graphed my point. Then I graphed my vector. And then I know that my vector is on, this vector is on the line that is represented by this equation. So this gray line here is the graph of this r of t. Okay? So now if we have vector r of t, 2 cosine t, 2 sine t, and 3. So looking here, if you see the 2 cosine and 2 sine, you might notice that is going to be a circle, radius 2. So circle, radius 2. And this 3 is our z. So that's going to be, that lets us know it's at level 3 on the z axis. So when I draw my circle, it's going to be a circle and it's at the 3 level. Now, sometimes people want to draw their, let me kind of sketch over here. Sometimes people are like, oh, 1, 2, 3. My circle must be on the 3. Well, I mean, I get why people think that, but let's think about how this, the axes look. So like I think about this, like if I was to get ground level at it, this circle, if I like say this, I had like a cup, like a cylinder, and I set it down, then the top of the cup would be at the level 3. I also think about like a graduated cylinder when I'm in a science class, and they always, like when I remember when I was in elementary school, and they were like, get eye level so you can, measure, get a correct measurement of the water and stuff. So that's what I think about here. Like it's going, like I think about if I was to get eye level with it. So, and you see it's a circle, radius 2, and it's at level 3, when z equals 3. Now, if we had, x was the constant, then our circle would go around that axis. And we'll talk about that in a minute, but with an ellipse. Okay, so now let's look at this. R of t, you have 4 cosine t, 4 sine t. You look at that like, ooh, it's a circle. But then you have this t. That's not a constant. So it doesn't tell me a level I'm going to be at. It is a t. So as t changes, the level changes. So it's like spiraling. So I call it's a helix. Some people just call it a spiral. And it's of radius 4. So t is the z component, so it's going to go around the z axis. So if, and obviously this is not a good look. Let me see if I can make my helix look better. Probably not, but let's see. So it wants to go around. You see the helix, it's going around. So That is going around the z-axis because the t is in the z component. If the t was in the x component, then our helix would be going around the x-axis. If t was in the y component, our helix would be going around the y-axis. Another thing is when our coefficients are the same, our shape is a circle. When our coefficients are different, remember our shape is not going to be a perfect circle. It'll be an ellipse. And this is what I just said. I had written it out. So when your t is in the x component, that lets us know that the helix is going to circle the x-axis or rotate about the x-axis, spiral around the x-axis. And then this next one, you see my coefficients were different. So this is an ellipse, and the helix would rotate about or around the y-axis. So getting those big ideas in our head. All right. So now we want to determine the vector equation for the line segment starting at point P and ending at point Q. So P can be x1, y1, z1, and Q, x2, y2, z2. So in order to find the vector, we can find the difference from going from one point to the other, because we're not starting at the origin, we're going from point to point. So this is what that vector would look like. The difference in x, difference in y, difference in z. So now we want to use the vector in one of the points. I'm just going to use the first point, so P, to write the equation of the line. So that's going to be the vector equation is going to be the point. I write it as a vector, x1, y1, z1, plus t times the normal vector here, which is, like we said, is the difference in x, y, and z. So now, here's where you have to kind of think this next part. So the x1, y1, z1 just is going to come down. With this t, we're going to say t with all the x2, y2, and z2 minus t with all of the x to the 1. So that's what this looks like. And so I wrote this, and I didn't have this 1 here at first. So I just want you to look. It was equal to this. Okay? So then, looking at this, I said, all right, well, this x1, y1, z1 is like having a 1. And so they're the same. This and this is like having the same variable. So I can now factor out 1 minus t and put that vector together. So that's what I did here. I did 1 minus t and put the vector plus this piece here. Okay? Now, if I wanted to say, well, what about I wanted to find something like vector r of 1 or a vector r of 0. So if I found vector r of 0, what that would become is 1 minus 0. So that's 1. That gives me x1, y1, z1. Then that would be 0 times that, so it's nothing. But now what if my vector was 1? 1 minus 1 is 0, so that whole thing would go away. And the second part would be 1 times x2, y2, z2. So looking at this, that tells me that these equations, I have the interval it goes from restrict t to between 0 and 1. And that would give me my x1, y1, z1 and x2, y2, z2. So notice how our vector r of 0 is the vector that goes to P, and vector r of 1 is the vector that goes to Q. So then I think this is the last thing we did, maybe not, but identify the surface described by this. So r of xy, so this is in two variables. If you remember, we had said before that when you have xy, that is your z. So just keep that in mind. So we have x, y, and then x squared plus y squared. So the x and y just is what it is. X equals x, y equals y, and z equals x squared plus y squared. And so x squared plus z equals x squared plus y squared is an elliptic paraboloid. That's what it asked. So yeah. But then I want to just kind of go over when you have a function of one variable, your y equals f of x. So y is a function of x. Or you can say x is a function of y. So you can change everything in terms of x here. And what we did in this r x y, we took z and put it in two variables. Z become x, a function of x and y. So here, z is a function of x and y. Now what about the x? X would be a function of y and z. So that means y would be a function of x and z. So it's what other variables that we're not, that's like y, you can't be in terms of y. So let's look at this in vector form. So r of xy, the xy would be your z. So notice g of xy replaced my z. G of xy replaced my z. Xy is z. Yz, that's going to be our x. So g of yz replaced my x. So then my last one is we'll look at xz. So xz would replace my y. Okay, so awesome things to look at. It should make sense. You just have to kind of sit and really let it soak in. That z is z will be a function of xy. Y will be a function of xz. X will be a function of yz. So I wrote this hyperbolic paraboloid, and I said y is equal to this function. So that means in the y component, that's what I'm going to put. So where the y component goes, I put this. And then x and z just is what it is. Okay? So I hope that was helpful.